Okay, so another example for determining probability distributions. The lottery Powerball uses 40 balls numbered 1, 2, 3, all the way to 40. All right, so that's usually how a lottery Powerball works anyway. So randomly a ball is, pulled out of a basket, and if you get all the numbers, you win the lottery. So let the random variable x represent the first number of a Powerball draw. So just the first number. Part A, find the probability distribution of x, which is the first number of a Powerball. And what is the probability that x is an even number? Okay. So with part A, you're used to me by now drawing up a table like this for a probability distribution. All right, this is addressing part A. So do this, I do this. And I put x here, which represents our sample space. And then we write the probability that our variable is each of these particular sample spaces. And then we have, what's our first number? Well, 1. So for a Powerball, all the options are from 1 all the way to 40, right? Dot to 40. Can you see how long our bar is going to be? Our table, it's going to be huge. We don't actually need to do it like this. This is unnecessary. Why is this unnecessary? I can explain. If we go ahead and determine the probability for each of these numbers, well, let's have a look. What's the probability of randomly selecting the number 1 in a basket with balls where there's a 1 there, then it's 2, 3, 4, 5, 6, 7, 8, 9, all the way to 40. You've got 40 balls in there. What's the probability? Well, it's 1 in 40. Because there's 1 and there's 40 balls in total. What about for drawing a 2? Same thing, 1 in 40. 3, 1 in 40. All the way to 40, 1 in 40. Every single number has the same likelihood of being drawn. There's a shortcut for this, right? When your random variable, which is the first ball being drawn, has what we call a discrete uniform distribution, that is, each of all of your options have the same likelihood or the same probability, you don't have to draw this massive table up. It's inappropriate, it's unnecessary, it's a waste of time. What we'll do instead is just write a single statement for part A, okay? The single statement will look like this. The probability that our variable will equal any of our sample space, right? 1, 2, 3, any number that can be drawn out, 4, 5, 6, all the way to 40, is just going to be the same 1 out of 40, right? That's all that is. So this statement is telling you that your variable, right, the first number, the probability of being any 1 to 40 is literally identical. They're all the same. They're just as likely. Now, what's a good way to communicate what those numbers are just to write a little comma and just to note that your sample space is from 1 to 40. And this is how I do it. 1, 2, 3, ... all the way to 40. Okay? That's part A. So no need to do a table for this one. And again, just to summarize, the reason why is because the probability of all of those numbers, 1, 2, 3, 4, 5, 6, 7, 8, all the way through to 40, they're all the same, right? 1 in 40. Okay, part B. What is the probability that x is an even number? Okay. Well, in a set of 40, right, from 1 to 40, right, there are 20 even numbers. So in this case, right, the probability that our variable in this case, which is the number of even numbers, is going to be equal to 20, because there are 20 of them, out of the total of 40, which is a half.